This video is on analysis of variance, but we're going to actually look at the situation where we have what we call randomized block design, or also known as ANOVA with repeated measures, or two-way ANOVA. How is that different from one-way ANOVA? Well, with one-way ANOVA, which we also call completely randomized design, we actually take independent samples, and each independent sample is assigned to one of the treatments. So say, for example, we were testing the performance of cars for different types of gasoline, whether or not if we put some additives in the gasoline, we may actually improve the MPG, the miles per gallon. And so we could take gasoline type A, gasoline type B, gasoline type C, D if we have four types, and then we will randomly assign units to those four types of gasoline. Those units or objects that we assign to the types of gasoline, so that would be cars in this case, would then, drive, and then we would measure the miles per gallon performance. Now, you would like to, of course, standardize where they drive if you could, but that's less important right now. The main thing is that the cars that are assigned to gasoline A are different from the cars assigned to gasoline B, different from the ones assigned to C and D. So it is completely randomized. So if we had 30 cars, we could just randomly assign the 30 cars across the four types of gasoline. So that would be completely randomized design. Randomized block design, however, wants to have some control over the factors that might explain the difference between the performance of the cars. So what you can do is that you could actually make your samples homogeneous by taking the same set of cars and assigning them the different types of gasoline to see how they perform. So if I took 5 cars, for example, and then I gave each of them gasoline type A and let them run until that runs out, and then somehow purge the system, then take the gasoline B, give to each of the 5 cars and let them repeat the experiment, and gasoline type C and gasoline type D, then in that case, the sample is homogeneous because I'm using the same cars and I'm repeating the experiment, hence the term repeated measures. So each car will give me performance for the different types of gasoline. So repeating gasoline A, B, C, D. And so we have repeated measures. The reason why we also use the term block design is because each car will give us a block of data. We refer to that as a block. So for the 4 gasoline performances that we have for a given car type, that would represent a block. Okay, we're going to see that in an example that I'm about to show you. But just before we get to that, let's just go back quickly to one-way ANOVA and just see how we're going to modify what we do in two-way ANOVA. Well, from one-way ANOVA to two-way ANOVA. And I think if we could get that, it won't be so hard. So in one-way ANOVA, the way in which we did our analysis was that we said, let's analyze variation. There is total variation, which we call SST, and we said that that was made up of 2 parts. The variation due to the treatments, so for example, in our case, if we're thinking of the types of gasoline, then it would be the variation due to the types of gasoline and what we cannot explain, which we will call the error variation. All right? And as I mentioned to you, we make the assumption that the populations are normal and that the variances are the same, or the standard deviations of the populations are the same. In which case, what we do is we try to estimate the population variance using the variation due to the treatments and the variation due to the error. And then to do that, what we would do is we'll calculate MSTR, which is the mean square, the mean square due to treatments, and the mean square is simply SSTR over the degrees of freedom. Let's just call it, in this case, DF1, because that would be the numerator. And recall that we showed a variance is sum of squares divided by degrees of freedom. If we now do the same thing for the error term, then we get MSE, which is the mean squared due to the error, which will just be sum of squares due to the error, and we excuse me, divide by the denominator degrees of freedom. In the first case, the numerator degrees of freedom will be the treatments minus 1, and then in this case here will be the total sample size, n minus k. This is just for one-way ANOVA that we're talking about. And recall that we would calculate an S statistic, which was the ratio of these two variances, MSTR over MSE. Okay? So that's what we would do. And if we sort of exceed whatever the critical value is, then we have evidence that the means are different. Now, what's different now with the two-way ANOVA? Let's take a look. So with two-way ANOVA, going back to our formula, we said that total variation is made up of the variation due to the treatments plus the variation due to the error. By using homogeneous samples or group that we keep repeating the experiment with, we could now actually further isolate another level of variation, and that is the variation due to the blocks, what we call the blocks. So in the context of the experiment involving gasoline and cars, if we repeat the experiment with each car, then a car becomes the block. So what happens now is that there's variation due to the cars. Like, say if I'm using a BMW, a Mercedes, a Toyota, a Lexus, or whatever, these cars have variation amongst them. So what we do now is the part that was the error term, we could further refine that and take out variation due to the cars. In this case, the cars are the blocks. So we separate that into SSBL, sum of squares due to the blocks, and what's left, we still refer to it as SSE, the error, what is unexplained. We may as well call it the unexplained variation. All right? And so now we have SST is made up of three parts. SSTR plus SSBL plus SSE. And that now will help to improve the sensitivity of our tests, because when we take MSTR over MSE for our S statistic, it does not include the noise that is created by the differences amongst the blocks, in this case the automobiles. All right? So you already had formulas for SST, SSTR, SSE, but we're going to sort of modify that a little bit. I'm just going to show you. We're going to expand that a little bit. Not modify, but expand it. So for SSTR, you already seen this one, which is NJ X bar J, that would be for the group or for the treatment, minus the grand mean squared. Now, interestingly, NJ represents the size of sample J, or treatment J, the sample size for treatment J. But because we're using a randomized block design, each group has exactly the same size, because remember what we're doing is we're using a homogeneous sample that we're repeating an experiment with. So if I have 5 cars, for gasoline A, there'll be 5 cars. For gasoline B, there'll be the same 5 cars. Gasoline C, the same 5 cars. So the 5 cars represents the blocks, which we call B. And so therefore we can replace NJ by B. And our formula will look like this. And because B is a constant, we could actually put B on the outside and then take X bar J minus X double bar squared. So that's what our formula looks like for calculating the sum of squares due to the treatments. Well, similarly, if we turn our heads 90 degrees, I think, counterclockwise, then we will now be looking at the variation amongst the blocks. So the formula for the calculation of variation among the blocks is actually very similar, and it would look like this. Move this around a little bit. So if we want a variation around the block, so SSBL, what it would have been if we allowed the sample sizes to vary, it would have been now the sum of NI. Why I? Because now I'm looking at the variation among the rows. Not the columns like we did for treatments, but for the blocks among the rows. And so it would be X bar I, which is the mean for that row, minus the grand mean squared. But because each row have the same number of treatments, in other words, each car gets the same number of treatments, and if there were 4 types of gasoline, so each car would get the 4 different types of gasoline. That's a constant. We refer to that as K, of course, which is the number of treatments. So I could replace Ni, which is the size of row I, by K, a constant. Because that's a constant, I could factor it out, because if I put it in here, that's okay, but I could factor it out. So I could just put the K on the outside, sum X bar I minus X double bar squared. And that will give me the sum of squares due to the blocks. Now recall that we said SST is equal to SSBL plus BL. Yes, we do want BL, but I don't want to put it first. So I'm going to say we always put our treatments first. SSTR plus SSBL plus SSE. There is a formula for SSE, but it's a little tricky. It kind of looks like this. It's not fun to look at. It's SSE is given by Xij minus X bar I minus X bar J plus X double bar squared. I believe that's what it is. I'm operating completely from memory here. And rather than use this formula, look at this. We could actually get SSE from taking from the total sum of squares, the sum of these two, SSTR plus SSBL. We could do that instead. We've already given you formulas for those. What's the formula for this guy? Well, the formula for this guy, we already know it. It's a lot more palatable than the formula for SSE. The total sum of squares formula is the same formula as if we were calculating the variance or the standard deviation of the overall sample. So SST is simply the sum over all Xij. I'm just going to use one summation. Maybe I'll use 2 because your book has 2. Xij minus X double bar squared. That's sum of squares. Right? Remember, that's the same thing that we use when we're calculating standard deviation of a sample. So all we're doing is calculating the standard deviation of the overall sample, but we will need the sum of squares for all of the values in that sample. But recall I gave you a shortcut formula, which I want you to use in this case, and the shortcut formula will be this. So SST will be over all ij, Xij all squared minus the sum, we have to use double summation because of I and j, of ij, and we put it all in brackets, squared over n. Doesn't that look familiar? That's exactly the same formula that we use, and we refer to it usually in a single sample problem that we did much earlier in chapter 3. We call it SSX, sum of squares due to x. Well, here we just call it SST in the context of ANOVA, the total sum of squares, but it's the same as the SSX for that sample if we were trying to find the standard deviation. So that, I think, is a lot easier for us to work with than this crazy looking formula over here. I'm sure you'll agree with me on that. So that's what we're going to use. We're going to use this SST, SSBL, SSTR, and then we will find SSE by simply doing arithmetic. And then we could solve our problem. Okay, so we have all the formulas. I should give you the degrees of freedom, however. We're going to need those. So for MSTR, that would be SSTR over the degrees of freedom. Let's call it degrees of freedom 1, in which case the degrees, let me not use capital. I need to be consistent. We normally do it with right, degrees of freedom 1. So degrees of freedom 1 in this case is just K minus 1. We already know that from before. Now, MSBL, if we wanted to find that, would be SSBL over DF, and that degrees of freedom, I'm not going to call it 2 because I normally use 2 to refer to the numerator degrees of freedom, which will be for SSE in this case. Let's just call it DF for now, right? So this will be B minus 1. So the number of blocks minus 1. Same way for treatments, we went the number of treatments minus 1. For blocks, we'll go the number of blocks minus 1, the number of rows minus 1. And for MSE, MSE is mean square due to the error, is SSE over its degrees of freedom, but the degrees of freedom is K minus 1 times B minus 1. All right? And then, of course, the overall degrees of freedom is N minus 1. So we have all the formulas that we need. Now we could actually go ahead and solve this problem. All right? So let's see. Let's look at a problem that we have. So here's a problem taken from your textbook. A research firm tests the miles per gallon characteristics of 3 brands of gasoline. I'll give you the context of 4, but here's our example has only 3. Because of different gasoline performance characteristics in different brands of automobiles, 5 brands of automobiles are selected and treated as blocks. Now, they didn't have to tell you that. They're making life too easy. But if you were told that the same 5 cars were used in the experiment, in the repetition of the experiment, then you should know that those are blocks. All right? So if car number A, is given gasoline type 1, 2, and 3, then that's a block. So that's how you'll be able to identify it. Now remember, I mentioned to you that we can indeed have one-way ANOVA problems that with balanced design. What I mean by balanced design is that the sample sizes are the same for all of them, but they're still independent. I've just decided to give them the same sample size. But in randomized design, you do not have to have exactly the same sample size. So I could, if this was completely randomized design, I could have 5 cars test gasoline 1, 8 cars test gasoline 2, 3 cars test gasoline 3. I could do that. It's not a problem. And that would just be an unbalanced design, but it's still a one-way ANOVA problem. Here, if I use 15 cars, 5 each, that is a balanced design, but still one-way ANOVA. Now I'm using 5 cars, but I'm repeating the experiment, and that's two-way ANOVA. So I hope we get the difference between one-way ANOVA and two-way ANOVA. And the benefits of two-way ANOVA over one-way ANOVA is that you're controlling some of the added variation. You're helping to extract some of the other noise, other forms of variation in the data by now isolating variation due to the types of cars. Before that, when we did a randomized design, we were not able to isolate variation among the cars. Now that we have actually kept the same cars and repeated the experiment, we can now isolate the variation due to the cars. So at alpha is equal to 5%, is there a significant difference in the mean miles per gallon characteristics of the 3 brands of gasoline? And so let's set up this problem, all right? So we're going to do it this way. We have gasoline 1, 2, 3. And 18, 24, 30, 22. 24, 30, 22, 24, 30, 22, 20, 21, 26, 29, 21, 26, 29. You should be taking notes same time as I. As I'm working through this, you should be sitting like you're in class and then taking the notes and doing this so that way you have it in your notebooks as well. 20, 27, 34. 20, 27, 34, 24, and 24. Good. Now we have the car would be type A, type B, type C, type D, type E. And so you can see now we have our blocks. The data, repeated data for car A, repeated data for car B, for car C, and so on. And so let's set this up nicely. So what we should do is we should note the size of the of each of the treatments. Well, the sample size for each of the treatments is the number of blocks that I have, which is the number of cars. So it's just 5, 5, and 5. And then the we could then calculate the averages of each of the treatments. Now you notice I'm doing calculations. I really should be setting up the problem and then come to the calculations, but that's okay. Let's do the calculations and then we'll just write the 5 steps. Okay, let's do that. It's kind of convenient to just do it now. X bar J, and we have 22.8, 22.8, 24.8, 24.8, and then 25.8. Good. We want now for blocks, so we're going to expand this here. So we will have I shouldn't say I, but K, because K will be the size of each block, the number of treatments. So it's just 3, 3, 3, 3, 3. And then we have to calculate the sample means for each row. Just add them up, divide by 3, and we have the following values: 19.67, 19.67, 25.67, 31, 23.67, 31, 23.67, and we have 22.33, 22.33. We also have the following. The grand mean, x double bar, will be the sum of all the xij's over n. I've calculated that to be 24.47. 24.47. I just use Excel to give me the values, just taking the average of those 15 numbers. You could do that. You could add them up, divide by 15. That will give you whatever the value is, okay? So we have x double bar. We have the sample means for blocks, and we have the block means and the treatment means. And I believe only other thing that we will need later on, well, when we do the calculations, we're going to need the total sum. We're going to need this xij, sum of all the xij's, and sum of the xij squareds, and that will be used to calculate SST. Cool? Good. So you have this data. I'm going to go and state the problem in our 5-step procedure. So now that you see this, two-way ANOVA is just an added step. It's not a big jump from one-way ANOVA. Once we get through one-way ANOVA, two-way ANOVA is just an additional step. So let's state our hypotheses. Hypothesis, step 1. So mileage performance are the same, average mileage performance are the same versus they differ. So HO, HA, since that's what we're interested in, so we could say mean mileage performance are the same for the different types of gasoline, right? Versus the mean mileage performance differ. So if they're the same, mu A is equal to mu, so not mu A, it's 1, 2, and 3. Mu 1 is equal to mu 2 is equal to mu 3. HA, at least one mean is different. At least one mean is different. So that's step 1. Cool. Step 2, the test statistic. F, our test statistic, is MSTR over MSE. So it hasn't changed, right? But what has changed is the degrees of freedom of MSE is now different. So DF1, which is numerator, is still K minus 1. DF2, which is denominator, is K minus 1 times B minus 1. All right, that's the difference between the two of them. Now we want to go to step 3, decision rule. So the decision rule this is alpha, 0.05. We want F critical. And we know that F critical is F alpha, DF1, DF2. So what's DF1? DF1 is K minus 1, which is 3 minus 1, which is 2. DF2 is K minus 1 times B minus 1. But we have 3 treatments, 3 minus 1, and we have 5 blocks. So that's 4 by 2 is 8. So our critical value is F, critical value is F critical is F.0528, which turns out to be 4.46. Okay, so if F observed is greater than or equal to 4.46, reject HO. Or if p-value is less than or equal to 0.05, we will reject the null hypothesis. All right, so that's our decision rule. Step 4, our calculations. So this is where we have some fun. Let's do a nice clean sheet for that one. So first thing we need is SSTR. SSTR, the sum of squares due to the treatments. Remember we said sum of squares due to the treatments would be B multiplied by B by sum of X bar J, X double bar squared. And that's, we just remove the B because it's the same for each term. So that would be 5. And then if you go back to the data that if you've written it down, for treatment 1, the treatment mean was 22.8. So 22.8 minus 24.47 squared plus 5. And then the second treatment mean was 24.8. 24.8 minus 24.47 squared plus 5 times third treatment mean was 25.8 minus 24.47 squared. When we work that out, we get a value of 23.33. If we continue for SSBL, SSBL is K times X bar I minus X double bar squared. Now there are 5 of them. I won't write out all 5. I'll just write the first and the last one. So to be 3 times the treatment mean for, not treatment mean, the block mean for block 1, which is 19.67. 19.67 minus 24.47 squared plus dot dot dot, meaning that I'm continuing, plus 3, that I'm going to do the very last one. And so you just have to repeat that because remember we already have all the 5 block means. 22.33 minus 24.47 squared. And that gives us a value of 217. So now the last thing that we need is the total sum of squares, SST. Total sum of squares, SST, as I mentioned, is just like SSX, xij squared, and sum of xij all squared over n. Now I will confess I have to just pause for a quick second to calculate what these values are. I'm doing it in Excel. Is equal to sum of the 15 values. I should have had it beforehand. And sum square of the same 15 values. Okay, so there we go. So I got it. It only took a second. So that turns out to be 9233 minus 367 squared over 15 values that we have. And we get a total of 253.73. 253.73. So now we have SST, we have SSBL, and SSTR. Can we find SSE? Absolutely. SSE then would be SST minus, remember I mentioned to you that we would take away from that the sum of SSTR plus SSBL. And so substituting the values in here, we will get SSE is equal to 253.73 minus the sum of 23.33, that was SSTR. SSBL is 217. And so SSE turns out to be 13.33. Good. So now we have everything that we need. All we do is we create our ANOVA table. Let's do that on a fresh page. The ANOVA table will be sources of variation, the sum of squares, the degrees of freedom, the mean square values, the F value, the F critical value, and the P value. And we have the following: treatments, source of variation treatments, blocks, error. So for treatments, it was 23.33, SS value. For blocks, it was 217.07. I had 217 earlier. 217. And then we have 13.33. Our degrees of freedom K minus 1 is 2. B minus 1, which is 4. 4 by 2 gives us 8. And then when we do our total is 253.73. Our total here will be 14. And the mean square values, so MSTR would be 23.33 over 2, which gives us 11.67. MSBL is 217.07 over 4, which is 54.27. And then MSE is 1.67. Let's find the F values. So we have actually in this problem, we can get two F values. One based on the treatments and one based on the blocks. The one based on the blocks would actually allow us to test the hypothesis whether or not there's a difference between the cars, right? And if there's a difference between the cars, then you could see why we really needed to remove that source of variation. If there was no difference between the mean performances of the cars, then perhaps a randomized block design is kind of relatively equivalent to a randomized design would be equivalent to a block design. But if there is a difference between the different cars, you would definitely want to have removed that error, that variation in the data, because remember we said that there are other reasons or other factors that could explain the differences in performance. So it would be nice to remove that and not make it a factor. So here we go. When we divide this value by the error, MSE, we will get the F statistic that is associated with treatments. It turns out that that is about 7.0. And then if we do the other one, we get 32.56. 32.56. So those are our two F values. The critical values, if we were testing just for treatments, based on the combination of degrees of freedom of 2 and 8, then we would have a critical value of 4.46. If we were testing for difference between block means, then we would have to use the combination of 4 degrees of freedom for blocks and the 8 degrees of freedom for the error. So we'd use F.0548. It gives us 3.84 as our critical value. The p-values, I just use Excel to give me the actual p-values. So I have 0.0175, 0.0175, and then 0.0001. So the p-value for blocks is actually significant. The p-value for treatments is also significant. So, but the question really is about, is there a difference between the performance, the mean performance for the different types of gasoline? But as a little bonus, we actually get to examine whether or not there's a difference in the cars as well. And you can see that there is a difference between those cars. So hence the reason why that kind of experiment was even more important. Okay, so let's do our conclusion. Conclusion 5. Decision. Conclusion. And so we say, since, if we do the critical value approach, since 7 is greater than, well, it's more, just strictly greater than, it's not even greater than or equal to, is greater than 4.46, or we could say since the p-value, since 0.0175 is less than 0.05, we will reject the null hypothesis. What do we conclude? There is evidence, sufficient evidence. There is sufficient evidence that the mean mileage performance, mileage, I'm missing an A, mean mileage performance for the types of gasoline differ. Okay? It differs. There you go. So, what kind of error might we commit? Type 1 error, because we rejected the null hypothesis. So, possibility of type 1 error of type 1 error, and then the risk of type 1 error, risk of type 1 error is 0.0175 or 1.75%. So we'll only be taking a 1.75% risk of being wrong, but we're allowed to take up to 5% risk, alpha. And so therefore we're safe. A couple quick things I wanted to add to this. One is that assumptions for ANOVA is that populations are normal. Right? Variances are the same. Population variances are the same. And then the sample, in this case it's just a single sample, is randomly chosen. In other words, you didn't pick a set of cars that you know would bias the results. So those are some of the assumptions that we make for this particular problem. What are the advantages of that kind of experiment? There's some advantages. One is reducing the sources of error or variation. Reducing sources of variation. Okay, or the factors that can explain the result, right, that we're trying to establish. That's one. Two, you need smaller sample sizes. So we didn't have to find 15 cars, we only needed 5 cars, and repeated the experiment 3 times. So that would actually have been cheaper than trying to get 15 cars. Okay? So those are the 2 big benefits of that: reducing error variation, or the sources of explanation, the number of factors that can explain the variation that we see, and then of course we need a smaller sample size. There are some disadvantages, largely what we call order effects or learning effects. But in this case, I am not exactly sure that those 2 are actually at play. So disadvantages: one, order effects; 2, learning effects; 3, fatigue effects. So what are those? Order effects. So sometimes the order in which we do the experiment. So if we use gasoline 1, then 2, then 3, does that affect the performance of the car? Do we use 2, then 1, then 3? Does that affect the performance of the car? So that would be order effects. Learning effects. Is the car learning how to use the gasoline better as we change it? Maybe not. And then fatigue effects. The car getting tired as it repeats the experiment. Now, in experiments involving human subjects, you tend to find those kinds of issues. So, for example, if we were, say, looking at the effect of training, or maybe different methods on the productivity of employees. So maybe we have 3 approaches or 4 approaches to assembling a particular device. When we're going to experiment by using the same employees. So we teach them method 1, and then we get them to do the assembly. Then we teach them method 2, do the assembly, method 3, method 4. So you could have order effects where so is a sequence of which method they use affecting the outcome. Then is learning taking place as they go through? Are they getting better and better? And not just because of the methodology, but because they're familiar with the task, and so therefore that is messing things up. Are they getting tired as they repeat the experiment? So those are some examples of the potential disadvantages, and they tend to show up more in experiments involving human subjects. How can you eradicate those? By going back to a completely randomized design, but then you have the disadvantages of the fact that you have other factors that may explain the outcome that you see. So you kind of have to balance those two things. So in terms of order effects, what you would do is to minimize it, you could randomize the sequence among the different subjects that you have in your experiment. And then that might actually scramble things a bit. And then, of course, you give them some time to rest before they do the next experiment. You don't just, okay, do one, now go ahead, do two, do the next one, do the next one. You might say, do one, okay, take a rest, come back 15 minutes later, come back. Then do the next one, another 15 minutes, 20 minutes later, in which case then you give people a chance to rest, okay? So that's two-way analysis of variance, and I hope the explanations were fairly clear. And any questions, feel free to ask. Thank you.